Hey, what's up, guys? This is Chung here again. So, and I want to talk about this 96 unique binary search trees problem. It's a very classic problem. It's, as you can see, it's got a lot of likes here. I'm gonna give my own likes here. Yeah, I think I kind of like this problem. Yeah, so the difficulty it's medium, but to me, I think this is more like hard to medium, between medium and hard. Yeah, I think it's pretty classic questions here. So let's take a look. So the description is very easy. You're given a number n. How many unique binary search trees can you get from 1 to n, right? See, he gives you an example here with 3. This one's the so first, what is a binary search tree, right? Binary search tree is the for each node for each node, the left for each node, all the nodes on the left side is smaller than the node value, and all the nodes on the right side is greater than the root value. So for n equals to 3 equals to 1 here, right? So for 1 you have 3 and 2 here, right? Because you cannot put 2 and 3 on the right side. You can only put on the right on the sorry, you cannot put it 2 and 3 on the left side because they are greater than 1. So that's 1. Same thing here. And then 3, 2, 1, 3, 1, 2, 2, 1, 3, right? It's pretty clear here. But how can we know how many unique trees we can get with the number n, right? I think the idea we're using here is by using the dynamic programming. Basically, and I'll try to explain this one here. Mm, here. Yeah, sorry. For some reason, my drawing software just just stopped working, so I just restarted. Okay, so back to this problem here. And so how can we deduce, right? Deduce the result from previous result. I think one thing we want to know, we want to okay, let's say for example with number 3, right? With number 3, so the first thing we want to deduce is 1, 2, and 3, right? So the total number with all these numbers with 1, 2, 3, the total subtree will be so basically we pick each one, we pick each of the element as the root element, right? Let's say, for example, if we pick 1 here, we pick 1 as the root, and then we pick 2 as the root, and then we pick 3 as the root. If we have the unique binary search tree for all the possibilities of the root node, and we sum them together, and then we get the result, right? We get the final result with n, how many binary search tree we need, right? So basically, the first loop will be, if we have a 3, we just loop from 1 to 3, right? How many we, with each node? With each node, will calculate the calculate by using this element as the root node, how many binary search tree this can construct, right? And so when it comes to this, like each root node, once we fix the root node, right, what we need to do. Let's say, for example, this one, right? With this one here, what are the nodes left, right? So with this one with the root, and then the right side is 2 and 3, right? So here we can only put 2 and 3 on the right side, right? Because they're both greater than 1. And on the left side will be basically will be empty, will be 0, right? How about 2 here? 2 here will be a 1 on the left side and a 3 on the right side, right? For 3, how about 3? So 3 will be the 1 and 2 on the left side, and the 0 and 0 on the right side, right? And the the number of the total unique trees that for this one, for example, this one, it's gonna be the number, the total number of subtree on the left side multiply the number on the right side. But basically, this is the final result will be the product of the left subtree and the right subtree. Let's say if this one is 1 and 3, right? So on the left side there's 1, and this one is 3, right? This is also 1. So 1 times 1 is equals to 1. With this one and 1, and this is 0, right? With 0, we also give it 1 because we don't want to make it 0, right? With 0, and then this is the what? This is like how many subtrees for two nodes, right? Two nodes is 2, right? 3 and 2 and 3 2 and 2 3. Same thing here, right? For 1 2, this is gonna also be a 2 here. It's gonna also be a empty is 1, right? So in total will be a 2 plus 1 plus 2, right? Equals to 5. So that's the total unique binary search tree for n equals to 3. And one thing keep in mind here, right? You need to do a mind jump from here. See, we don't care about what are the nodes number here. We don't care about if it is 2 or 3 here, or it's 5, 6, or whatever. All we care about is how many nodes on this side, right? As you can see here, so 1 and 2 and 2 and 3, they're different numbers, but they're both 2 nodes, right? As long as they are 2 nodes, we know that it will have 2 binary tree that these 2 nodes can construct, right? So, and as you can see here, so now, and 1 is obviously is 1, right? And now, since we remember, we have calculate. Oh, why the weight is different? Fine, different. Never mind. I think this is better, right? Yeah, this is better marker here. So, as okay, remember, see, we have n equals to 3 here, right? 3 is what? Equals to 5, right? So what does it mean? It means that 3 numbers or 3 nodes can give us 5 unique binary subtrees, right? Let's assuming we have this 4, 5, 6, and blah blah blah, right? When we deduce this kind of numbers there will be a case that the left subtree will be what? Will be 3 nodes, right? Whatever, 1, 2, 3, 4, 5, 6, or something, or 3, 5, 3, 5, 4, right? So in that case, we don't need to care about what are those numbers. We know, okay, with 3 nodes, we will have 5 nodes, right? Oh, sorry, we will have 5 unique binary search tree, and then we can just use that, right, to build up from bottom up, right, to build all the result we need, right? For example, 4 here, right? With 4 here, the left side will be 1 2 3, and then here will be 4, right? And then we know 1 2 3 will have 5, so we can do a 5 here, and here will be 4 with 1, right? So it's a 5 5 times 1 will be 5. So for this like for this like uh, for this root for this node as a root, we'll have this result, right? This is I hope you guys understand. So I know it's a it's not a easy I know it's a not easy explanation to understand, but yeah. Okay, so let's try to code it. So the code surprisingly is very simple. All right, so like we said, okay, we need to have a array here first to store all the previous result, right? So we have a DP here, and for the DP array here, we do a 0, right? Because for we want to initialize with 0, and the length will be n plus 1. Why? Because remember we have a on the one here, right? On the one here on the left side, we basically it means 0. It doesn't have any node, right? So but we still want to use this as 1, right? Because we don't want to be 0 0. We still want to have a value for the 0 node, right? So that we can use that to time with the other side. That that's why we need a like 0 at the beginning. And we know that 0, we want to give it a 1, right? We want to make it a 1. Because, like I said, we don't want to, 0 times 2 will be 0, right? We don't want to do it. So we want to give it a 1 here. Because 1 times whatever on the right side, it won't have any effect. And that's 0 node. And for the 1 node, we already know the result, right? It's also 1. Because with 1 node, you can only construct 1 tree, right? That's pretty obvious. And now we will need to uh, loop the rest of the n numbers, right? For range. Now we need to loop from 2, right? Remember, we already have the result for 0 and 1, so that's why we'll have 2 here. And we'll loop until the n here, so n minus 1, right? Sorry, n plus 1. Okay, remember what did we say? So with the number I here, so we want to pick all the possible numbers within this range here, right? Within this range I here, and we use each of them as a root, to calculate, and then in the end we sum them together. So how do we pick the each node, right? So basically we just loop through from the beginning to the current I, right? So we're gonna use a j here in range, right? So we want to start from 1, right? From start 1 to I, to I plus 1. Why? Because we don't want to start from 0, because 0 means 0, it means it doesn't 0 means there's no node, right? Basically, remember this 1 means the first number, right? The first number of this I here. And if it's 0, 0 means there's no node, and we want to we want to pick at least one node as the root, right? So, and what do we do here? So with DPI here, that's the DPI is the current result, right? For this node, right? For the number I here, right? How many unique subtrees, binary subtree we can construct, because we are summarizing all the results for each node, right? Remember here, so what do we do here? Remember, the number value itself doesn't matter. We only care about how many nodes on the left side and on the right side, right? Since this is the index, right? So the index means, and the index starting from 1, right? So what does it tell us, right? So that's the root index. So any numbers from the index 1 to the current root number, that's how many, that can tell us how many nodes on the left side. And so how many nodes on the left side, right? that will be the j minus 1, right? That will give us j minus 1. It's the number, how many numbers on the right side of the current root j, right? And then we need to times the number of nodes on the right side, right? How many? Because we know we're calculating for the current I, right? So on the right side, there will be I minus j number, sorry, j, right? Number of nodes, right? So left side number of nodes and the right side number of nodes. And then we just do a product, and then we just summarize all the results for each node, for each root, right? Within range I. Yeah, basically that's it, right? I mean, and then in the end, we just return, right? We just return the dp what? dpn, right? Because we're creating n minus one, I'm sorry, n plus one number of nodes, and it's zero base, right? Zero base, which means that the n, it will be the last node, the last number, right? Yeah, sorry, in range. 3, 5, submit. Yeah, voila. See, pass. Pretty easy, right? But the thinking process is definitely not easy. It requires some really, really deep thinking here. Okay, recap what we have discussed, right? Using the dynamics programming concept, right? And then what? And then for each I, for the current I, how do we calculate its or the unique binary search tree for the current I? We try all the numbers, right? We try all the numbers within I. We use each of them as the root. Since the root is different, so we can make sure the result will be unique, right? And then we do what? We do a left node, right? This is I basically. Left side I here. That's the J. Sorry, this is J. There will be a left side of node and the right side of node. So for each node, because we need to try each of the element within I range to be the root, so we can have all the results. For each of the J here, we find how many nodes on the left side and how many nodes on the right side. Remember here, so the value of the nodes doesn't matter. All we care is about the number of nodes, right? And then we do product of them. We get the current result of the number of the trees with with j as the root, and then we sum everything to the I here, and then we get the result of I, and then we can just keep using it from here. Then in the end, we just return the last element in our DP array. Cool. Yeah, hopefully I do a decent job or a okay job to explain this problem. I know it's not a easy problem, but try to understand it. I think it's pretty cool problem. Yeah. Okay, cool guys. I think that's it for today. Thank you. Yeah. Bye.